Hey, I'm Kishore Angani, and my co-presenter Sheetal Mehta couldn't make it here. We are from the video platforms group at Yahoo, and today I'll be talking about video transcoding on Hadoop. Right. So this is a brief outline. I mean, we'll be talking about video transcoding on Hadoop, the current architecture. Then there were some new requirements and how we actually worked around our limitations of the old architecture, and then got into a generic master worker pattern for YARN. Well, so what is video transcoding? So we have these multiple formats of videos coming in. I mean, they could be from publishers, which are huge movies, and then there's UGC content, and these are like in many formats, which is we almost have 10 container formats, 40 video, and then 60 audio formats. So what we actually do is we then convert them into standard MP4 or WebM for consumption of our apps, I mean, consumption within our apps on multiple devices. So apart from these, there are also enrichments, which are like watermarks, previews, thumbnails, visual seek, and then of course there are a few machine learning jobs. And all of these are extremely I/O and compute intensive. So so much so that the SLA is actually measured in multiples of the source video length. For example, FFmpeg takes anywhere between half X to about 5 times the video duration. It of course depends on the configuration of the tool and resources available. And the computation requirements are extremely source and destination sensitive. And as to the parallelism, I mean, there are some jobs which can be done on fragmented videos, but many of them require the whole file to be present for optimal results. So this is what our DAG actually looks like. So the first phase is where we actually download the source video, and then there's a decision taken to actually fan out into multiple transcode or enrichment jobs. And then finally, there's a cleanup job, right? So what's important here is that we do take a decision after the first phase. So this is where the job split happens, and we decide how many downstream jobs we actually have to do after that. And so the rate is about, we receive about tens of thousands of videos a day. Duration variance is huge. I mean, it could be anywhere between 10 seconds to 2 hours. And of course, there are a few gigs to a few MBs again. And the output fan out could be anywhere between 5 to 15 jobs per source video. So these are about 100,000 jobs that we process every day. And a static DAG plan actually leads to either heavy resource wastage if we over provision the DAG, and resource contention if we like under provision, I mean, if the DAG is very strict. Well, so what are we doing? So we're currently using Hadoop 2.3, and this is our current architecture. So the API hosts actually feed into an OZ queue, which actually schedules the first parent map-reduce job. And this is where the mapper actually downloads the file, and then the splits are generated, and decides how many downstream MR jobs to actually start off. And the transcoders and the enrichers, and of course some of the machine learning jobs run as a mapper in the child MR jobs. And then there is the cleanup phase, which we have, and the notification phase. So why Hadoop? So the reason is, one, it is extremely reliable as a framework, extremely good resource management. We can ask for anywhere between 2 gig to 6 gig containers. And the downstream job resources are actually planned based on the source video. And of course, we have a distributed file system. It is elastic. Fault tolerance, UZ provides the job level fault tolerance, and then the framework provides us the task level fault tolerance. And then the log reporting and analysis actually runs as MR jobs on the same system. So everything is like nicely contained in the same Hadoop MR ecosystem, right? And then of course, it's extremely low maintenance, and it just lets us focus on whatever core we are actually doing. And this is fairly good for big jobs, wherein if there's a transcode for a couple of hours, this is fairly good. So now we have new requirements where there's UGC coming in. And UGC has extremely high variance. Bit rates, sizes, durations, and people would actually want to see the video surface. So, yeah. And the SLAs here, based on the MR framework, were very bad because, MR is actually designed for batch kind of processing, and we do see latencies of up to 50 seconds. So primarily the latencies are in scheduling the job, getting the first MR to run, and then scheduling the multiple MRs. So we do have latency just in scheduling, getting the job to start. And then we have a tiny latency in setting up the container with all the models and all those things that are required over there. And I try to emphasize again here, which is the job split is very important for us, because without that, we'd be wasting a lot of resources. And well, this latency is well known, is well documented, and there are alternate frameworks available. So our basic requirements, delta T1, you reduce by having some real-time scheduling, and the delta T2 if we actually reuse our containers. So what do we do? We actually explored Thales, Storm, and Slider. Well, most of these frameworks are actually optimized for captive data flow, which is data flowing through the framework as such. But in our case, it's actually metadata that flows through the framework, and the files are picked off either HDFS or the local file system. And this metadata is not exactly a clear indicator of the type of, the size of the job that you're actually processing. So most of the smarts that are given by the framework can't be used here. And the problem with video processing is you cannot do it line by line. There is no key value decomposition, and many of the jobs actually require that the whole file be present locally. Well, so this is a basic comparison of what we've seen. With our current architecture, latency was high, high in terms of only for the small videos. And container pre-warm was taking up some time too. Now, Thales gives us a DAG, which is very good. But the problem is, it's again with the scheduling. So where we can't be over-provisioning the DAG, neither can we under-provision the DAG. And Storm, the problem was getting good container locality, and basically container release is not there, there's no container isolation, and the jobs could be stepping on each other, and the resource management is fairly coarse. Slider, there is actually no DAG, and there is no job or task abstractions. So that is why we actually rejected that too. So what do we do? We decided to go our own way. So we decided to have a master worker framework, which is a generic YARN application. And it's extremely simple. So the master manages a pool of workers, and these could be heterogeneous. And all it does is reads jobs and distributes them over RPC to the workers. And you can have a pluggable scheduling strategy, which will manage the number of workers that you want to run, and custom resource allocation for each worker type. So if there's a job which is small, you can actually ask for only a 512 MB container, and you can go up to whatever the max size is. Right? And the worker resources are set up once at Bootstrap. So all the resources are actually downloaded from HDFS, left onto the local, the container is prepped and ready. And these are long-running resources, long-running containers, so the jobs are executed one after the other, and most of our latencies disappear here. The state management is done by the master, and it is dumped to the HDFS. And of course, there's security and token management, which the whole harness provides. So eventually, what you can actually do is just plug in your master code and some worker code and a scheduling strategy, and the jobs are actually scheduled in real time and sent over RPC to the workers. So this is a simple interface that we have, which is the master just implements, a couple of functions, and the worker implements the execute method. And these are custom classes that you can give it to it, give to the framework. So this is how our new architecture looks like. So the API hosts actually feed into a job queue. The master plugs off the queue and feeds the jobs over RPC to the workers. And the workers are actually doing their job, and the state information is actually persisted to HDFS. Now we organize one master and multiple workers into a pool, and there's a client managing multiple pools, because just in case the AM goes down, the master goes down, you could have the other pools working, and when the master comes back up and restores its containers, it's back working. And you could have multiple clients running on multiple clusters, so that way you would have a large-scale system which is working. So the main advantage it's giving us is you can have time to lives, you can have jobs processing, you can say recycle the containers after 100 jobs are processed, or recycle the containers once every 7 days, because that's a security concern in Hadoop. And you can have heterogeneous containers, you can have multiple pools, you can have adaptive container allocation and release. So currently we use a low and a high watermark based scheduling strategy. So depending on the load, the containers are, the workers are actually adjusted in numbers. And this has given us significant improvements in latency, in the sense that the jobs actually get scheduled within milliseconds. And YARN and client, YARN also has AM fault tolerance. So when the AM goes down, YARN does spawn the AM again. And the clients the client actually takes care of the other fault tolerance. And of course, the master takes care of the fault tolerance for the workers. Well, so what next? We hope to release this soon. And if we get decent scheduling strategies and everything, we can be very close to what Google Containers is doing. And of course, from Yarn, we would love to have multidimensional scheduling and node labels for resources like GPUs and so on. Thank you. Questions, please. Yep.
Step up to the mic. Sure. Good. Hi, I have 2 questions. First, are the jobs just like shelling out to a copy of FFmpeg that runs like natively on the Linux system, or is it like a Java binding? Like how is the encoding actually executed?
So basically, it's a lot of binaries. I mean, there's some which are open source, there's some which are proprietary, there are machine learning algos, and so on. So the transcoding is just one aspect of the whole thing. There's enrichments, there is scene detection going on, and there's a lot of ML jobs trying to figure out various things in the video. So it's a mix of open source and proprietary systems over there.
And then have you explored going any deeper, like demuxing the video and trying to work in chunks of frames at a time to really spread out the per video parallelism?
Yes, you could do that for a few jobs. I mean, for example, if you're generating something like a preview, you would want the whole file to be there for the preview to be optimal. So it depends on what type of a job is actually running over there. Yeah, it actually.
I don't know if there's anything in practice that you actually experimented with, like found it if it worked at all. I'm sorry, just the trying to parallelize the sub-video segments, if that increased efficiency in any kind of notable way.
So for transcoding, that will work. But like I said, for some of the other jobs, it will not work. So eventually, when it comes to the SLA, I mean, we were actually counting SLA from receiving the video to all jobs done. So the SLA is the most important thing that we're looking at here. Distribution, yes, you can distribute. I mean, it depends on the job, like I said. So transcode, you can. But some of the other jobs you can't.
Thank you.
You're welcome. Any more questions? Thank you.